Welcome to today's GATE video. Myself, Dr.T.SANGEETHA, Assistant Professor, Department of Mathematics, Sakuntala Ammal Engineering College. Today's topic, heat equation, one-dimensional heat equation on partial differential equation. First, introduction about partial differential equation. PDE involves, PDE means partial differential equation, involves partial derivatives. Partial derivatives means two or more independent variable. Normally differential equation having one independent variable and more dependent variables, because the partially differential equation two or more independent variable and two or more dependent variable. Next, used in physics, engineering and mathematics. Example, heat equations, wave equations and Laplace equations. Next, the formation of partially differential equation. Formation of partial differential equation. First, elimination of arbitrary constant. Second one, elimination of arbitrary function. First one constant, next functions. Next the order, highest derivatives order, because of second derivative, third derivative and highest derivatives order. Degree, the power of highest order derivatives. That means n equal to 2, 3, 4, 5, 6, etc. nth derivatives order. Next, the classification of partial differential equation. So first one, first order partial differential equation. First order partial differential equation means first one, the function u of x comma y, the function u of x comma y, then the derivative, first order derivative ux. Next, the second order derivative is equal u double x, the differentiate with respect to x 2 times. Next, the higher order derivative u triple x, u 4x, etc. Next, the based on highest order derivatives having heat equation and wave equations. Next, second order partially differential equation classifications. So first one, elliptic equation. Elliptic equations means it is a Laplace equation. Second one, parabolic equation. Parabolic equations means heat equation. Next, hyperbolic equation means wave equation. These equations are based on the discriminant, the equation b square minus 4ac. Next, parabolic equation. Parabolic equation, it is also called heat equation. So the first we general the form a u double x. U double x means second order partial derivative. So a is a constant plus b into uxy. Uxy means the partial derivative with respect to x and y plus c u double y. So a, b, c are constant. A, B and C are constants. Next, maximum use the formula if b square minus 4ac equal to 0. It is a parabolic. Parabolic means it is a heat equation. Next, the heat equation is parabolic type. The mainly use the partial derivatives u x, u x y, u y y, etc. So these are higher order partial derivatives. Next, physical meaning of heat equation. So first thing, describe heat flow in your body. So first the physical meaning, heat flow in your body, our body temperature, maximum the heat equation based on the temperature. Next, the based on Fourier's law. Next, the temperature varies with the time and position. So today morning to evening the temperature varies the position based with the time. Next, one-dimensional heat equation. Today topic, one-dimensional heat equation. So the first standard form, dou u by dou t. It is a partial differential equation. Dou u by dou t is equal to alpha square. Alpha square means the thermal diffusivity. So alpha square into dou square u by dou x square. It is a second order partial derivatives. Next, the initial and boundary conditions. So the first initial conditions, u of x comma t. So u of x comma t, t is a time, based on a time. So the total of the condition u of x comma t is a temperature. Next, alpha square is equal to thermal diffusivity. Next, first solving the heat equations. First case 1, the solving the heat equation, steady state solution. So first we discuss about the steady state solutions. So first one, definitions. We say that u of x comma t, the mainly content u of x comma t is a steady state solution if ut is equal to 0. It is a initial time based on the interval 0. That is, u is time independent. Next, if u of x comma t is equal to u of x, the function u of x comma t is equal to u of x is a steady state solution to the heat equation, then the initial conditions, these are initial conditions. So first ut is equal to 0 implies c square u double x is equal to ut is equal to 0. C square means thermal diffusivity. So implies ux is equal to 0, u double x is equal to 0, because the formula ut is equal to 0 implies c square u double x is equal to ut is depend on the time is equal to 0 starting the interval 0 comma l. L means the interval, L means time, long time. So ut is equal to 0, u double x is equal to 0. It is a second order partial derivative, u double x is equal to 0 implies the main condition is the heat equation, steady state heat equation, u equal to ax plus b. Steady state solution can help us deal with inhomogeneous, means non-homogeneous. Homogeneous equation is equal to 0. The non-homogeneous equation is equal to having any functions. With in non-homogeneous, Dirichlet boundary condition. Dirichlet boundary condition. Note that first the initial condition u of 0 comma t equal to t1 is a time independent and time dependent. Next, u of L comma t. So 0 and L are interval. Next, the t is based on the time. So implies the first condition b equal to t1. Next, al plus b equal to t2. So the overall implies u equal to value t2 minus t1 divided by l in the x plus t1. Next, solving the heat equation in homogeneous Dirichlet boundary condition. Now consider the heat problem. First one, ut equal to c square u double x. It is a c square is a thermal diffusivity, u is a function with partial derivative x and second derivative equations u double x. U of 0 comma t is a initial condition t1 and the boundary condition u of L comma t is equal to t2. Overall the function f of x is equal u of x comma 0. Next, the given interval x 0 less than x less than L. 0 to L is a interval t greater than 0, time based. Next, 0 t greater than 0, 0 less than x less than L. The x variable starting from 0 to L. Next, step 1. Let U1 denote the steady state solution from above. From the above, we denote U1. So, U1 equal to the condition T2 minus T1 divided by L into X plus T1. Next step 2, let u2 is equal to u minus u1. U condition here, u equal t2 minus t1 by L x plus t1. So u1 condition is t2 minus t1 divided by L x plus t1. Next step 2, let u2 is equal u minus u1. So subtract from u minus u1. From to u minus u1. Remark, by superposition u2 still solve the heat equation. Finally we getting the heat equation solving the condition u2. Next, the boundary and initial conditions satisfied by u2 are, first one, u2 of 0 comma t. It is a interval value 0 and that based on the time t equal u comma t minus u1 comma 0 equal to condition t1 minus t1 equal to 0. Previous, because u1 condition t2 minus t1 by L into x plus t1 and u condition t2 minus t1 by L x into t1. So solving these both conditions, we getting the value. Finally u2 of 0 comma t is equal to 0. Next, u2 of L comma t, boundary condition. L, first the initial interval 0, the final interval L, comma t is equal u of L comma t minus u1 of L. Because of it is initial, it is a by a boundary. So equal to t2 minus t2. t1 is initial condition, t2 is boundary condition, is equal to 0. So u2 of x comma 0 equals f of x minus u1 of x condition. Step 3. Solve the heat equation with homogeneous, because previous one is inhomogeneous Dirichlet condition. Here solve the heat equation with homogeneous Dirichlet boundary conditions and initial conditions above. These also homogeneous because of the homogeneous equation is equal to 0. So these are homogeneous Dirichlet boundary conditions and initial conditions. This u2 of 0 comma t and u2 of L comma t. Step 4. Assemble u of x comma t equals u1 of x plus u2 of x comma t. Remark, so according to our earlier work, limit t tends to infinity, u2 of x comma t is equal to 0. So we call u2 of x comma t the transient portion of the solution. So we have the limit condition u of x comma t implies u1 of x at t tends to infinity. T means time based, so t tends to infinity, that is the solution tends to the steady state. Next example, solve the heat problem. So the given conditions are, first one ut, the condition, the function ut equal 3u double x. Next, the initial and boundary conditions are u of t comma 0 comma t equal to 100, u of 2 comma t equal to 0, because of the given interval 0, given interval 0 to 2. Given interval 0 to 2. So t greater than 0. So 3 is F, thermal diffusivity. So because of C square equals 3. So C equals value root 3. Next, the initial condition, the interval 0 and 0 varies, the interval varies from 0 to 2. So, the boundary, the initial condition u of 0 comma t and boundary condition u of 2 comma t, also given the values are 100 and 0. Finally, the function u of x comma 0 equal to 50. All the conditions are given. So we have c equal to root 3. So c square equal to 3. The condition c square is a thermal diffusivity. Here c square equal to 3. So we getting c equal to root 3. Next L, the interval, last interval, L equal to 2. So x varies from 0 to 2. So we taking L equal to 2 and T1 equal to 100 because u of 0 comma previous one u of 0 comma 1, the condition u of 0 comma t equal to T1. So T1 condition given value 100. Next u of L comma t, here that problem 0 comma 2 comma t is equal T2. The condition, initial interval 0 and T1 and T1 equal to 100. Next, the last interval 2 and T2 equal to 0 and f of x, the function value is 50. So all the values are given. So c equal to root 3, L equal to 2, L equal to interval 2, the initial interval 0 and T1 equal to 100, T2 equal to 0 and the function f of x is equal to value 50. Next, the steady state solution is u1. The condition of u1 equal T2 minus T1 divided by L into x plus T1. It is u1 condition. So T2 value is 0, T1 value is 100, L value is 2 into x plus T1 value is 100 equal T1 minus f of x into x. So f of x value is 50. So 100 minus 50 into x. So the value. So okay. So solve this term. We getting 100 minus 50x because 100 divided by 2 is 50, 50 into x plus 100, then we write 100 minus 50x. Next, the corresponding homogeneous problem for U2 is thus, first one, the given condition ut equal to 3 u double x, u of 0 comma t equal to u of 2 comma t is equal to 0 conditions. Next, u of 0 comma x comma 0 equal 50 minus f of x is equal to value 100 minus 50x. So the common term 50 minus 100, 50 minus 50 minus 100 plus 50x equals 50 minus 100 minus 50 plus 50x. 50x minus 50 equal the common term 50 taking out remaining x minus 1. So the condition 50 into x minus 1. Continues that problem according to the problem with P equal L equal to 2. The sine series for 50 into x minus 1. This already given the exercise problem. Given the exercise problem with P equals L equal to 2, the sine series for 50 into x minus 1 is 50 into x minus 1 is the condition minus 100 by pi summation k equal to 1 to infinity 1 by k sine into 2k pi x by 2. It is a sine series condition of 50 into x minus 1. So that is only even modes occur since lambda 2k is equal c 2k pi by L equal to root 3 k pi. So u2 of x comma t is equal, substitute the value minus 100 by pi summation I equal to 1 to infinity 1 by k e power minus 3 k square pi square t into sine k pi by x. So apply and substitute these sine series equations and values. Finally we getting hence the series u of x comma t is equal u1 of x plus u2 of x comma t equal 100 minus 50x minus this condition u2 of x comma t, that substitute this condition 100 by pi summation k equal to 1 to infinity 1 by k e power minus 3 k square pi square t into sine k pi by k pi x. So previously applied the conditions of sine series for 50 into x minus 1. So the condition is this one. Next apply the condition of u2 of x comma t. Then finally we getting the value of u of x comma t is equal this value. Next, homogeneous Neumann boundary condition. Solving the heat equation, homogeneous Neumann boundary condition. So let us consider the heat problem. Ut is equal to c square ux. It is a general form. Ut is equal, ut means dou u by dou t is equal c square into dou u by dou square u by dou x square. This one is so dou u by dou t is equal c square dou square u by dou x square. So c square is a thermal diffusivity. Next, the initial and boundary conditions are ux of 0 comma t is equal ux of L comma t is equal to 0. So both are, it is initial and boundary condition is equal to 0 because of the interval 0 to L. Next, the main condition u of x comma 0 is equal to f of x, in which we assume the ends of the rod are insulated. As before, assuming u of x comma t is equal to x of t into t of t is the system. So x double dash, it is a second order differential equations. The complement x double dash minus k into x is equal to 0. So the initial and boundary conditions also x dash of 0 equal to x dash of L equal to 0. Then we get the function value t dash minus c square diffusivity k into t is equal to 0. So note that the boundary condition on x are not the same as in the Dirichlet condition case. Next is solving for x. So that previous problem solving for x. Case 1, first case 1, k equal to mu square greater than 0. So we need to solve x double dash minus mu square x is equal to 0. The characteristic equation, we assume the auxiliary equation, we taking the value r square minus mu square equal to 0. Because of it is a homogeneous equation, so taking the condition is 0 implies r equals r square minus mu square equal to 0. So r square, taking opposite side, it is mu square. So r equal to plus or minus mu. So it is a root of characteristic equations which gives the general solution. So the general solution of complement function. So x is equal, both are different roots because one root plus mu, another root minus mu. So taking the constant value c1, the general solution a e power r1 x plus b e power r2 x. So r1 value equal to mu, r2 value is minus mu. So writing the general solution, x is equal c1 e power mu x plus c2 e power minus mu x. The boundary conditions tell us that 0 equal x dash of 0 equals mu c1 minus mu c2 because e power x is equal to 0. So e power 0 value is 1. So e power minus 0 is value is also 1. So finally mu c1 minus mu c2. So 0 equal to x dash L equal, put value x is equal to L. So first one x is equal to 0, so the initial condition. Next one the boundary condition, x is equal to L, we getting the general solution mu c1 e power mu L because of x is equal to L minus mu c2 e power minus mu L are in matrix form. So it is a matrix form, mu minus mu. So first initial condition, next mu e power mu, it is e power 0, e power mu 0, it is also mu e power mu 0. So x is equal to value 0. So e power mu 0 is 1 minus mu 0 is also 1. So mu minus mu. Next to this condition, mu e power mu L minus mu e power minus ul. In the constant coefficient c1 c2 is equal 0. Since the determinant is mu square, so this determinant mu square common term, so taking out remaining e mu L minus e power minus mu L, it is not equal to 0. We must have c1 c2 equal to 0 and so x is equal to 0. So the value c1 c2 is equal to 0. So finally we getting the x value congruent 0. Case 2, k equal to 0. We need to solve x double dash equal to 0. Previous one x is equal to 0. Now we need to solve x double dash equal to 0. Integrating twice gives x is equal c1 x plus c2. So x double dash means integrating. So x is equal, the general form c1 x plus c2. So the boundary conditions give 0 equal x dash of 0, x dash of L equal to z1. It is a initial, so boundary condition. Taking c2 equal to 1, we get the solution x is equal, x not equal to 1. Next case 3, k equal to minus mu square less than 0. So we need to solve x double dash plus mu square x is equal to 0. Then the characteristic equations, the previous one taking, the characteristic equation r square plus minus mu square equal to 0. Here r square plus mu square equal to 0. So taking the opposite side, going to the opposite side, r square minus mu square. So minus means it is a complex, imaginary. So r equals plus or minus I into mu. It is a complex root. So complex root, the auxiliary normal general function x is equal e power alpha x into c1 cos beta x plus c2 sin beta x. It is a normal general form. Here we taking the general solution x is equal to c1 cos mu x plus c2 sin mu x, because only imaginary root only getting the alpha equal to value complex root alpha plus or minus I beta. Here alpha equal to value 0, alpha equal to value 0, beta is equal to value mu. So apply this general solution. X is equal e power 0x, because alpha equal to value 0 into c1 cos beta value is mu cos mu x plus c2 sin mu x. So e power 0x value is 1. So finally we getting the general solution x is equal e power 0x value is 1. So remaining values are c1 cos mu x plus c2 sin mu x. So which gives the general solution x is equal to c1 cos mu x plus c2 sin mu x. So it is a case 3, k equal minus mu square. We getting the general solution x is equal to c1 cos mu x plus c2 sin mu x. Next, case 2, k equal to 0. So the value general solution value x is equal to 1. Case 1, k equal to mu square. We getting the general solution x is equal to c1 e power mu x plus c2 e power minus mu x. So the first solution, first example about steady state solution. So case 1 and case 2. Second one, inhomogeneous, because inhomogeneous means non-homogeneous direct like boundary condition. So having some functions for RHS side. Next, solve the problem. Next, homogeneous Neumann boundary conditions. All the problems solved using the heat equations. Next, the boundary conditions. First one, 0 equal to x dash of 0 boundary condition, mu c1 sin 0, because the value x is equal to 0. So sin 0 plus mu c2 cos 0. So sin 0 value is 0. In trigonometric formula, sin 0 value is 0, cos 0 value is 1. So this term fully 0, we getting mu c2. Next, C2 equal 0. So the condition C1, C2 is equal to 0. So mu into C2 is equal to 0. Therefore, the condition x dash of 0 equal to 0. Next, 0 equal to x dash of L, the interval L, mu C1 sin mu L plus mu C2 cos mu L. So the value minus, because of C2 value is 0, so only getting this value, this C2 equal to 0, so getting the value minus mu C1 sin mu L. In order to have x does not congruent 0. This show that we need sin mu L equal to 0. So implies mu L equal to sin value n pi. 0 value is n pi. Mu equal n pi by L. Taking C1 equal to 1, we obtain, we getting the condition. Remark, we need only n greater than 0 since cosine is an even function. So we taking only even function. When n equal to 0, we get x not equal to cos 0 equal to 1, which agree with a k equal to 0 result. Next, derivation assumption. Because the previous problem, first homogeneous rod, next no internal heat source, constant cross section, heat flow along S direction only. Derivation final equation from energy balance equation using Fourier law. Fourier law means using the cosine series and cos series, sine series. Obtain the main condition dou u by dou t. The condition dou u by dou t implies ut, taking this condition c square. C square means thermal diffusivity. It is also alpha square is thermal diffusivity. C square u double x. So this condition using all the problems. Next application, heat conduction in rods, mainly application heat conduction in rods, cooling of metals, diffusion processes, financial mathematics. Advantages of heat model: predicts temperature distribution, used in engineering design, helps in material analysis. Conclusion, heat equation is parabolic partial differential equation. So parabolic equation is also known as heat equation, solved by separation of variables. Each variable solved by separation. Important in science and engineering, widely applied in real world problems. Thank you. Continue on next video.